Hey guys, how you doing? This is it, the last one of these videos that you have to watch. I think you'll come to miss them. Maybe not this one, because my nose is stuffy and I'm going to sniff more than usual. And I find that pretty annoying, so probably you do too, but I'll shut up and I'll get down to business. I will say, though, I hope that before watching this, you were watching the January 6th hearing, because that's history going down right now in your lifetime. You should be watching. Anyway, on we go. Here's your list of objectives. I think this is pretty representative. It says perform the basic operations. Yeah, you definitely got to do that. That's a pretty big chunk. Solve simple matrix equations. Yeah, true. Determinant of a 2x2. You're going to need to do that. Determinant of a 3x3 using both methods. I don't remember if you have to do both. One or the other might be good enough, but you better study both just in case. Find the inverse of a 2x2 by hand, definitely. Solve matrix equations involving inverse matrices, for sure. Use matrices to solve systems, including 3x3s, yes. Use matrices to find the area of a triangle, yes, you need that. Is there anything on the quiz that's not on here? I don't think so. I think that's pretty comprehensive. So on we go. Why isn't that working? There we go. Alright, so first we're adding matrices. This should be the easiest thing of all. Literally, you just grab matrix A and you grab matrix B, and to add them, as long as they have the same dimensions, you can add them. You just add them by adding the corresponding elements. So clearly here, you are looking at a matrix that has, let's see, 2 rows, and then you count the number of columns. I see 2 of those. So that's 2x2. I know that was obvious, but obviously for a different matrix, this is the same way you'll figure it out. Like matrix E over here. You're counting the number of rows first. So count the rows. There are 2. Then you're counting the columns. Count the columns. There are 3. So that thing's 2x3. Obviously, if there's a question where I ask you for the dimensions and you say 3x2, that is not close enough. That is dead wrong. No credit. So make sure you know how to do that. Alright, so now to actually do the sum. Because they're both 2x2, you can add them, and the result will be a 2x2, and you literally just add the corresponding entries. So you're just going to get what? 6, -5, 3, 3. Alright, super proud of us. That was really great. Moving on. So for this one, you're multiplying by a scalar. So grab matrix B. Doesn't matter who the dimensions are, or what the dimensions are. If you're multiplying by a scalar, you essentially just distribute 3 onto every single entry. So it'll be a 2x2 again. You'll get 12, -3, 6, 0. What could be easier than that? Not much. A times C. Now we're getting there. So grab an A, grab a C. Alright, these guys do not have the same dimensions, and that's fine, because for the product to be defined, we said you just need the inner dimensions to match. So what's this guy's dimensions? 2x2? What's this guy's dimensions? Well, there's 2 rows, but only 1 column. So we check to see those inner dimensions. This 2 right here is a counting of the number of columns we have, right? So that's how many things are in each row. There's 2. Then this first 2, that's the number of rows we have, which is counting the number of things in our column. And so since those inner dimensions match, you can see we've got that 1-to-1 ratio of entries in the rows to entries in the column. So we'll be able to do our little algorithm and find a product. Great. Now, what will the resulting matrix be? That's when you look at the outer dimensions. Our resulting matrix will be 2x1. So you know you're going to get a matrix that only has 2 entries in it. And those entries are going to live here and here. It's going to be 2x1, just like this guy, okay? So now, didn't want that to be so dark. Let's make it a nice minty green. No, can't see that at all. How about a nice creamsicle orange? Yeah, that's good. Alright, so what do? Well, you literally multiply the first row by the first column, and that'll give you the entry in the first row, first column. Now when I say multiply these, you're essentially doing the dot product. The dot product is when you multiply entry by entry and then add the next entry times the next. Oh, I'm bad at that. Sorry, my bad. Obviously we're going 2 by 4. Oh, this pen. 2 by 4. Then we're going to add to that the next entry times the next entry. So -4 times 3. That's giving me 8 take away 12. That's giving me -4. I will put that in my matrix in position row 1, column 1. All right, now that we are trying to find row 2, column 1, we'll just slide down and we'll use row 1. We'll multiply by, frankly, the only column we have. But we do the exact same operation. It's like a dot product, so it's 1 times 4. And we'll add to that 3 times 3. So I'm looking at a 4 plus a 9. That is a 13. In goes my 13. And this matrix is the answer. Oh, you can't use your calculator. I was going to say it's a pretty big deal that you show your work since you'll have your calculator, but you won't. If I didn't explain this well enough, your quiz is going to be a part 1, part 2 kind of deal. And so part 1, you will have no calculator at all, no access to your calculator. And that's where all the problems are. Part 2, you'll get a calculator. And the only thing over here is going to be the 3 by 3 matrix equation from a word problem. That's part 2. So literally, I'm talking about, on this review at least, the Chand problem. Part 2 will literally be one question, and it'll just be the big word problem that you have to write a 3 by 3. You have to write a 3 by 3 system first, convert that to a matrix equation, and then and only then can you use your calculator to solve the system. Obviously, I'll get to 16 when I get there, but that's going to be the breakdown of the quiz. Why did I get off on this tangent? I think I was explaining that showing your work is important. It's slightly less important because you won't have a calculator to do the work for you. So I can sort of trust that you know what you're doing, but guess what? You better show the work anyway, or else I'll be marking you down. I'm going to move on now. Bonk. All right, so this one's a little weird. 2, 4, 1, 3. Oh, so this is matrix A. So this funny notation here, if you haven't picked up on it, these vertical bars that don't have the little bits on the tops and the bottoms, this is a symbol that means find the determinant of matrix A. If you didn't know that, now you do. We're after the determinant. Now, since this thing is 2 by 2, finding the determinant should be a piece of cake, although I will jump forward and allude to when we do the determinant of a 3 by 3, I don't know, apparently the diagonals method had a more fancy name. It's called the method of Saris. That's interesting, right? It's just the diagonals method. But in that diagonals method, don't we multiply down a diagonal, down a diagonal, down a diagonal? And then don't we multiply up a diagonal, up a diagonal, up a diagonal? And we end up doing the sum of all the blues and the sum of all the pinks, and then when all is said and done, you do the difference of the blues and the pinks. Well, guess what? To find a 2 by 2, you're doing exactly that, just small, on a small scale. There's only the one diagonal to multiply down, and there's only the one diagonal to multiply up. So you do it. 2 times 3 makes 6. That's a 6. Then as you multiply up, 1 times -4 makes -4. And there are no other diagonals to multiply, so we can't really do a sum. So I guess by the time I get my red and by the time I get my blue, I just subtract. So this becomes 6 plus 4, it's 10. I don't know if I'm overcomplicating this, but if you think you might have trouble just memorizing our formula, which by the way our formula is ABCD, if you're after the determinant of that, you literally just do A times D minus B times C. That's the formula. If you're not into memorizing, then it might be nice to notice that we're doing the exact same thing we do for the 3 by 3. It's just a smaller matrix. so there's not as much to it. You only have to do A times D, and then B times C, and then subtract the results. That's it. That's how you find a determinant. Moving on. A times E. Let's see. Here's a matrix A. Here's a matrix E. Can these even be multiplied, you say? And the answer is, I don't know. Check the row by column. If there's two things in a row and two things in a column, then yes, we can. What do you expect the final answer to be? Well, if this is 2 by 2 and this is 2 by 3, then again, the inner dimensions matching, that's great, but it's the outer dimensions that tell us that when we're done multiplying here, we're going to get a matrix that is 2 by 3, which means we're expecting an entry here. Oops. We're expecting an entry here, 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 and here. Right? Great. Let's do it. How much work do you reasonably need to show? It would be nice. You're going to have a ton of room on this quiz because it's a short quiz, but maybe you could build me a little 2 by 3 workspace, right? Let me move this over so it's not getting blocked out by my handsome face. But again, for the entry in row 1, column 1, you'll grab row 1 multiplied by column 1. How's about you at least do this? -6 plus -4, -10. Slot it in. Let's do row 2, column 1. So I guess I'm, oh, come on. I guess I'm dropping that down. And I'm going to multiply row 2 by column 1, so I get a -3 plus 3. That's a 0. 0. All right, let's do row 1, column 2. So we're now doing 4 plus 4. That's 8. In goes the 8. Row whatever, column whatever. Row 2, column 2. That's looking like a 2 plus a -3. Show your work. It's not that hard. 2 plus -3, -1. Zip. Next. Row 1, column 3. That's gonna be 0 plus 8. That's 8. So another 8. Last, and we'll find out whether or not it's least, is 0. Not doing so hot. 0 plus -6 is -6. So it's last, but it's not least. There's your matrix. We did it. Moving on. A little bit tedious, but doable. All right, what about AD? You grab matrix A, you grab matrix D, and mercifully, we don't have to do this one, because if I try to multiply row by column, they don't line up the way they're supposed to. So undefined would be the answer here. Product is undefined, exclamation point. And again, the reason that's happening is because we've got this 2 by 2 matrix, but this guy is a 1 by 2. So those inner dimensions do not match up, meaning the number of entries per row is not equal to the number of entries per column. So we move on. 7, B plus D. Grab the B, grab D. Well, what a shame. Sure would be a shame if someone tried to add a 2 by 2 with a 1 by 2. You can't add them, because the way you add matrices is everybody's supposed to have somebody that it corresponds to. And so this is sum is undefined. I don't care. Okay, you guys get it. Moving on, 8. So this guy is a subtraction problem with a little built-in scalar multiplication. So -2. This is a 2 by 2 and a 2 by 2. Multiplying by the scalar isn't going to change the dimensions, so we'll still be 2 by 2 and 2 by 2. So this difference will be defined. So we got to do this one. This matrix would be unchanged for negative 1, 2, and 0. I prefer to just leave this as subtraction and distribute the 2 as a positive, although I suppose you could turn this into addition and distribute the 2 as a negative. So just go negative 4, positive 8, negative 2, negative 6. Maybe I do prefer that. Let's do that. It doesn't matter. You guys should understand that if you left this minus and distributed the 2 as a positive, of course you get the same answer as sort of making this a positive, adding negative 2, distributing that. Let's just do that. We'll get a 2 by 2 whose entries are 0 and 7 and 0 and negative 6. That's what I'm getting. Hey, if I'm getting these wrong, you could leave a comment on the video and I could go, yeah, you're right, that is wrong. And then future people watching the video would know that I've made a mistake, because you know I make mistakes all the time. So it sure would be nice if you guys maybe pointed my mistakes out in the comments. You could put a timestamp. You could be a hero, right? All right, moving on. Number 9. This is a little different. I don't think there's anything quite like this on the actual quiz, but I'm asking you to solve a matrix equation, and this is different. But I'm hoping you see that if you're solving for A, and this is just matrix addition, then 3 plus 4 times A would equal 43. None of the other entries matter at all, because with matrix addition, the only entries that really interact with one another are the ones that are in the same positions. So row 2, column 1, row 2, column 1, row 2, column 1. So you can just pull out those few values and write yourself a basic algebraic equation. So you know that 3 plus 4a would equal 43. And you just solve that equation. So 4a equals 40, a equals 10. All right, so that would mean that by the same token, if you wanted to solve for b, you'd focus only on the entries that are in row 1, column 1. So 2 plus 4 times 6 would equal b. None of the other entries matter at all. They're just window dressing. So for b, we can pull out the equation 2 plus 4 times 6 equals b. 2 plus 24 equals b. 26 equals b. That's it. You're done. Okay. 10. 10 is, I want to say similar, but it's not really similar, because here the operation happening was addition. That meant everybody just interacted with the other entries that are in the exact same position. Here we have a more complicated deal, where if you wanted to solve for C, the only way you're going to write an equation involving C, you're sure as heck not going to say that C times negative 2 is equal to D, right? You're not going to say that. That would be wrong. What you'll say instead is the row containing C multiplied by the row containing these things equals D. Except you're not going to do that, because then you'd have two different variables, and that's bad. So what if instead you knew that C was in row 1? You don't have to mess with the entry that's in row 1, column 1. You could mess with the entry that's in row 1, column 2 by using column 2. Right, kids? So be smart like that. Then you can solve for C without having to mess around with D. We can't have two unknowns. Two unknowns would be bad. But thinking that through, you can see now that we'll get an equation where C times 4, or 4C, plus is the algorithm, 6 times 1, so 6, equals this entry, the 50. So you get 4C equals 44, so C is 11. Zoinks. Alright, then you would solve for D in the same kind of way. Is there any tricky way to get after D? I don't think so. I think to find D, you now actually have to use row 1, column 1, but C is not a variable to us anymore. We now know that C is worth 11. So we can now write an equation where C times negative 2, or negative 2C, plus 48 equals D. But we know C. C is negative, or it's 11. So negative 22 plus 48 equals D. Taking 22 away from this would leave 26. Yeah, that's it. So that's a little different from the way we solved matrices before. Hopefully that made sense. For 11, okay, finally we're finding the determinant of a 3 by 3. This first method, method A, that method of Saris is the diagonals method. So you might notice that if I actually go to multiply down my diagonals, then down this diagonal I get 3 entries, like I would expect. Then you go to multiply down the next diagonal, and oh, geez, I only get 2 entries. What's supposed to be right here? Well, hopefully you remember that part of the algorithm here was to take this first column and just kind of append it down here on the end of the matrix. And then you see that this second diagonal should be 6, 1, 0. If you can just remember that obviously that should be a 6 and a 1 and a 0, then I guess that's cool. But I'd probably like to see you just adding the row. By the way, we go down this third one now, and oh look, it's 5, and we've got the 2 now. But I wonder what's supposed to be here. Oh yeah, I'm supposed to take this column and move it over. 6, 3, 2. So it's 2. Oh, they're both 2. That's kind of annoying, but that's okay. I don't need the third column because we only want 3 diagonals. So I don't need this other column. That would just give me the 1, 3, 4 again. So don't bother. Yeah, okay, anyway. So what I want to do now is get all 3 of these red products. I'm going to try to be nice and say you don't have to show a million bits of work. Like writing 1, 3, 4, that's pretty darn tedious. So sure, let's go ahead and say that a reasonable person can assume that you know what 1 times 3 times 4 is. It's 12. Now we're going to add all 3 of these products. So it's 12 plus 0 plus 5, 2, 2 is 10 times 2, 20. So there's our first sum. Now the rule is do the difference of all of the products on these other 3 diagonals that go up, 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 like this. So that's going to give us 0 plus 2, 1, 1, 2 plus 4, 2, 6, 8 times 6, 6 times 8 is 48. So there you go. So the sum of all this stuff in red is a 32. The sum of all this stuff in blue is a 50. And we do want the difference. And it's perfectly fine for determinants to come out negative. That's not weird, that's normal. So this is negative 18. That's our determinant. And I think I already double checked that on the calculator, so I'm pretty confident that that's definitely right. So let's move on. Click. So we're doing the exact same matrix. We already know the determinant is 18, but the question is, how do I find that using this other method called expansion by minors? And we said to do expansion by minors, you pick a row. And I think we've pretty much universally only ever done row 1, but you can do row 2, you can do row 3. Let's do row 1 again, just for demonstrative purposes. All right. So the way this works is you take the entry here, the 1, and then you multiply that by the determinant of the matrix that remains if you get rid of the row and column that the 1 is in. So if you kill the row and the column that the 1 is in, then 3, 1, 2, 4 would be the minor matrix that remains. So I'm going to go 3, 1, 2, 4. And I'm going to find the determinant of that matrix and multiply it by that entry there that we excluded. Multiply that by 1. Then you do that again for the next entry. So this time the 6. So this time we go 6 times the determinant of the minor matrix, which will be 2104 this time. Then you do that again, this time with 5 as your multiple. And you multiply by the minor matrix 2302, or the determinant of the minor matrix 2302. Now I've been leaving out signs, and I'm leaving out the signs because depending on what row you choose, you have a different pattern of signs. We said that across row 1 you go plus, minus, plus, meaning this 1 just stays plus. Then you're subtracting 6 times da da da. Then you're adding 5 times da da da. If we had chosen to work across the second row, then our sign pattern would be minus plus minus. Now I've said that a few times, but I've never actually done it. So I think it would be a good idea after I'm done doing this the once. Let's do it again, but across row 2. Maybe even do it across row 3 as well, just because, well, I have more time now, so maybe we should. Anyway, what's this going to be? This is going to be 1 times 12 take away 2. Remember, the determinant is 12 minus 2. I say it's 12 minus 2. I'm putting emphasis on the minus because a second ago when we were doing matrix multiplication was this times this plus this times this. There's little fiddly rules, a lot of little rules where you might forget, when am I supposed to add, when am I supposed to subtract? Best thing you can do is practice a bunch. And hey, if extra practice is something you were interested in, hold on, I'm coming. Hey, if extra practice was something that you were interested in, haha. Hey, if extra practice was something you were interested in, could you go to Delta Math? Sure, you could. You could go to whatever our page is, pre-calc. And there's still this assignment up for matrix review, right? So I don't know what the heck you want to practice, but if you wanted more practice multiplying 3x3 matrices, click on this. Here's a problem. Do it. Enter, enter, enter all the matrices. Say submit. You've got these videos too, so if this video featuring me isn't good enough and you forget how to do this, you could watch this video, see if this gentleman's any better.
Multiplying matrices 3x3 only. So a 3x3 matrix times another, multiply our answer. So we're going to be always multiplying by the middle row of that
He's pretty good.
Matrix. And then again, third row of our answer, then we'll...
He's pretty good. Anyway, just reminding you of all the things at your disposal. Hopefully it's overkill, because hopefully you feel like you understand this stuff pretty well anyway. Where was I? I believe I was doing this problem. Okay, we're going to go minus 6 times 8 minus nothing. We're going to add 5 times 4 minus nothing. So this is a 10, take away 6 times 8 is 48, plus 5 times 4 is 20. So this is negative 38 plus 20 is negative 18. Shocking. We got the same answer. So we must have done it right. All right, I said I would do this again, and I'm a man of my word. Doop. Okay, duplicated it. Clear. Nice. All right, so how does this look if we had chosen to go across row 2? I guess that just means that now my coefficients are 2 times the determinant, 3 times the determinant, and 1 times the determinant. And the minor matrices for 2, I'd be killing the middle row and the first column. So the minor matrix this time would be 6, 5, 2, 4. And the minor matrix for the one that has a coefficient of 3, zip, would be 1, 5, 0, 4. And the minor matrix this time is 1, 6, 0, 2. And the big thing that I wanted to make sure, the whole reason I'm doing this again is to remind you that across row 1 there was a sign pattern that said plus, minus, plus. But across row 2 the sign pattern is minus, plus, minus. And across row 3 the pattern would be back to plus, minus, plus. But that means our sign pattern says this negative applies to the 2. It's basically telling you not to subtract, but to change the sign of 2 to negative 2. Then it's telling you, okay, go ahead and add this term now. And now go ahead and subtract this last term. So now we have everything we need. Now we can do this. And we're looking at negative 2 times this thing's determinant, which is 24 take away 10, so 14. Then we're going to add 3. and 4 take away nothing is 4. Then we're going to subtract 1 times 2 take away nothing is 2. So we're looking at negative 28 plus 12 take away 2. So that's negative 16 take away 2. That's